Yes, Bismillah Rahman. We are going to have a discussion about waves and superposition. Actually, this chapter is again not a single chapter, it's a complete section. And in that section, what we have to learn that is we have three main areas what we have to discuss. One is the general waves, right? That is just a sort of revision. There are few new topics in that one, but we have or which we have to learn. Second topic is superposition, which is basically divided into two parts. One is its diffraction, and the second part of that is interference. Yani we have to talk about these two combinedly. They are not separated out. They are having the combination. And then we have to talk about stationary wave. This is totally the different chapter and the new chapter because we have not learned anything in the previous any previous level of either IGCSE or O levels or any other level. So you have to be very careful about this one. But overall weightage of this chapter is huge. Almost 25% questions are there which are coming from this topic, yani from this section or this topic. And in that one, almost 7 to 8 MCQs are there. How many? 7 to 8 MCQs. And the question which is asked to you from theory, it is from 8 to 12 marks. Okay. So by this all profile you have to tackle with this waves and superposition. So talking about the general waves, when we will talk about general waves, actually, first of all, we have to know about what is a wave and what is it, what is the behavior, what which is called a wave, what are the types of the waves, yani either longitudinal wave motion or transverse wave motion or electromagnetic waves or mechanical waves, etc., etc. Then two new topics are there in this topic, and in this chapter. They are, rather I will say, three new topics which you people have not learned before. They are the phase difference and path difference. This is one of the property of the wave. And secondly, Doppler's effect is new topic for you, although that was studied in your space physics in your IGCSE, but that is in detail here. Doppler shift, red shift, and blue shift is also here. And third is the polarization. So these three topics are new. Rest all is your previous revision. So if I talk about a wave, wave is nothing just like a disturbance which is taken place or which has taken place in the medium due to vibration of the particles. So I can simply say that when I disturb the particles in a medium, those particles propagate energy from one point to another point without the transfer of the particles from one point to another. That is called the wave motion, or that is called the wave motion. For example, if this is the particle which is in the hand of this person, and that person is going to vibrate the rope up and down, then what will happen? The particle which is in his hand or her hand, it will remain at the same position, but the energy will be propagated from this portion of the rope to the end of the rope, to this hook or to this nail. It means that all the energy is being propagated from source to, this is actually what, this is your source, and this is what, this is your yani, we can sing, we can call it sink, but it's not just the term in waves, but the energy is propagated from the source and that spreads out. Here I have shown that it is spreading out in one direction. So this is basically the direction of energy propagation, right? What is that? It is direction of energy propagation. Got it? So main thing you have to consider that energy transferred without the transfer of matter from one point to another point, that is called the wave motion. So here are two main types of the waves, right? They are the mechanical waves and the second type of the wave is non-mechanical waves, right? One of them is mechanical wave, and the second one is your non-mechanical wave. Mechanical waves are those waves which need a medium for their propagation. Very simple to understand. Those waves which need any medium, and medium is basically, you know, required almost for those waves in which the vibration of particle is required. But there are some waves, I will talk about those waves in the next slide. The waves which are the mechanical waves, they are your um, water waves, they are your spring waves, they are your surface waves, etc., etc. So these all waves are the waves which need a medium for the propagation. Are you getting it? Okay.
Yes.
The next is the non-mechanical waves. Actually, non-mechanical waves are classified as all electromagnetic waves, are photons.
Yes, sir.
They, yes, Mohsen, are you back? Okay. So non-mechanical waves are electromagnetic waves. They do not need any medium. This is very important. They do not need any medium for the propagation. Then why? Or how do they propagate? They are basically, they depend upon the field. So we can simply say that they are field dependent, right? They are field dependent. Field means either there are three four fields which we have to take care of, and out of three, two are mandatory. One is your magnetic field, second one is your electric field, third one is your gravitational field. So these waves are basically depending upon electric and magnetic field. So they are the electromagnetic waves. That's why they can travel in the vacuum, and their speed is same as the speed of light in vacuum. Yani 3.0 into 10 is about 8 meter per second. And most probably, you know, you people have learned about this all. I believe so. It's not a new thing for you, that they have this is an electromagnetic spectrum, right? If I'm not wrong, this is what, this is your electromagnetic spectrum, right? And that spectrum is basically the spectrum of all these non-mechanical waves. So these non-mechanical waves have different yani these waves have different frequency, because you now that every wave has this trait or this property that there will be frequency of the wave and there will be wavelength of the wave. So these waves which are electromagnetic are the which are non-mechanical, those waves are basically the waves in which the frequency varies from gamma to radio waves, right? With they move from okay. So I was talking about that gamma rays have the highest frequency, then X-rays, then ultraviolet, then light, then infrared, then microwave, then radio wave. This is the order of your electromagnetic spectrum or your non-mechanical waves. Okay, is it clear to all?
Okay, sir.
Okay,
Yes, sir.
so we have to consider this all in such a way that when we are talking about yani there is a question from, you know, if you remember there was a question of estimation. If you remember that, estimate the uh, range of frequency for infrared, estimate the range of frequency or wavelength for uh, red light, etc., etc. So that will help us out in different ways, that we have to figure it out, that yes, what is the wavelength and what is basically the frequency range of all these waves, right? Is it clear to you? Is this clear to all?
Yes.
When I move to this, that I told you that the I mean, I have shown this in this on the slide, that the wavelength of these waves increases as we move from gamma to you know, gamma to radio. So at gamma rays has the highest frequency and shortest wavelength, and that wavelength is 10 power minus 20 meter, which is very, very short wavelength. And wavelength of your radio waves, that is almost yani 1 kilometer. 10 power 3 is actually 1 kilometer. So in this way, we have estimation of that the waves have this much frequency. Uh, I mean, is my voice lagging or is it fine?
It's lagging a bit.
Yeah, now is it clear? Because
A bit
internet
more.
signals. Now is it clear?
No. A bit, yeah.
Okay. Okay. So if you get any problem in the voice, you can tell me in time. Okay. Then visible.
Sorry, your voice is um, a problem.
Hello.
Yes, sir.
Now, do you hear me?
Yes.
Okay. There is some internet issue on my side as well, not only in Quetta, here in Islamabad as well. Okay. So when we move to that these waves travel due to the vibration of electric and magnetic field. So I told you that these are the field forces. So both E and magnetic, yani electric and magnetic fields, they have a right angle to each other. Yani they are mutually perpendicular to each other. So I can simply say that when they are mutually perpendicular to each other, these waves are having two components, right? Are two vectors, electric vector and magnetic vector. Is my voice clear now?
Yes, sir.
Yeah, yeah. Okay. So actually, this wave looks like this. If you see this, I have to show you that this golden line is the direction of propagation of the wave, and on that line there are the black lines, these which are the magnetic components, and these all the electric components, and these electric and magnetic components basically swirl or whirl around. So here is that if you see the electromagnetic wave or electromagnetic beam from the back, you will see that it is spreading out in all directions. So that is why what do we do? We say that in these waves are spherical waves, right? These waves are spherical waves. So this was basically the sort of waves. Now we will talk about the waves, type of wave motion, right? Type of wave motion. So type of wave motions are two, and this topic is basically based the on the direction, sorry, on the motion of the particles on the wave. Got it?
Yes.
Okay. So if I say that there are two types of wave motion, longitudinal wave motion and transverse wave motion. So longitudinal wave motion is that motion in which the particles vibrate parallel to the direction of propagation of the wave. You knew this for a long time. Every student knew this. But just it's a revision. That's why I would make it short and smooth. That wave motion in which the particles vibrate parallel to the direction of propagation of the wave, that is named, or that is called your longitudinal waves. And especially these waves travel in the form of compressions and rarefactions, and their examples are sound waves and spring waves, when the spring is compressed and uh,
So,
just released.
what type of wave is a gravitational wave?
Oh, G wave. What a question, man. Actually, these are the field waves. I told you, na, that those waves which are having which do not have any particle to travel, or with who they do not need any particles to travel, they are called yani they are the non-mechanical waves. Gravitational waves are also some sort of non-mechanical waves. That is why the gravitational waves do not need any medium to propagate through, and they can travel, or they can be propagated even in the space where there are no particles.
So, more like, are they transverse or longitudinal?
They are transverse waves. It is
Uh,
said till now that they are transverse waves. Okay, but because we are not having sufficient information about gravitational waves, this topic is this needs a lot of discussion, that we still could not find the way, yani the gravitational force carrier, the particle which was responsible to carry, or which was responsible to transfer the gravitational force. That's why we cannot study the behavior of gravitational forces, sorry, gravitational waves till now. But it is said that they are transverse waves. But those waves which are seismic waves are, right, the waves of earthquake. They, in those, they, we have two types. One component is the P waves, parallel waves, and the second one are S waves. So they are different in compression, yani they are longitudinal and transverse. So in transverse wave motion, yeah, is your question clear? Should I move forward?
yes.
Okay. So the transfer wave motion means the vibration of particles is perpendicular to the propagation of the wave. Like, it is very, interesting that waves traveling in the string, waves traveling in the rope, waves traveling in the spring when it is moved up and down, and waves traveling in the water, and S waves in the seismic waves, or in the earthquake waves, they all are actually the transverse wave motion. So they travel, or we can represent them in the form of crests and troughs. Is this clear to all?
Yes.
Okay. Now, this is really, really important thing for any important topic to now. That is the characteristics of wave, right? What is that? That is the characteristics of the waves. There are several characteristics which are known to you. There are several characteristics which are new. That is why I will blend them all, and then I will let you know. Okay, so those characteristics, which are very basic, I will not get in detail of them, but those characteristics which are at advanced level, and we have to learn them in in detail because we are asked some questions from them. Those I will talk about in detail. Okay, so wavefront is the first representation of your wave, and for that, for the wavefront, actually you must have some background knowledge of few different topics, which are in which one is the phase and the second one is your position. But I will simply say that though these are the imaginary lines which join all the particles, or which represents all the particles which are at the same position and at the same energy level of the wave. For example, we believe that all the peaks are uh, when we join all the peaks, we get a wavefront. When we join all the peaks, we get a wavefront. So wavefront is basically that line which joins all the particles of the same position and same energy level of any wave. So they are usually represented by either straight lines or curves, right? So there are two type of wavefronts, right? Those are, here I have shown one, the other can I can show you here. They are circular ones. Okay, these are the circular ones like this. These are the circular wavefronts. For example, you, if you have seen, when you throw a stone, then the ripples are being produced, and those ripples are producing the wavefronts. Got it? Is it clear to all?
Yes.
Okay, now the next thing which is very very important, I mean, I really have a concern with this topic, but unfortunately I could not draw 7 8 diagrams which are required to explain it, but I would simply tell you what is required in from this all discussion or from this all topic. If tell you that these are some points on a string, and all these points are basically, this is 0 1 2 3 4 5 6 7 and 8 points are there, yani 8 particles are there, and these all particles are at the equilibrium position without disturbance, they are at the mean position. Then when you will propagate the part energy, when you will disturb them, all the particles will be disturbed from the main position, one after another. Is it? And when they will be disturbed after one and one after another, then those particles will strive to come back their equilibrium position, and due to that there will be a vector, motion vector generated of those particles, and that motion vector or that position vector, or you can say that vector, can be represented by the arrow. And I have shown you two diagrams in which 2 points, yani 2 parts are there. I have mentioned 2 parts. All those parts in which the wave seems to be having a positive slope or up the slope, there the particles after being disturbed, they move in the downward direction, their full direction vector is downward. And all the parts of the wave in which the particles, it seems that the particles went down before disturbance or before the equilibrium position, or they were shifted downwards from the equilibrium position, they will try to come back to the equilibrium position. So in this way, their direction vector will be upward arrows, and all the particles which are at peaks, they have nothing to show, they are best just momentarily at rest. So you can say that those particles are at rest. So I have shown this all here, that from the equilibrium position, all the green particles, yani I have represented with the color scheme, all the particles which are represented by the green, they are at the part up slope or positive slope, they have downward motion vector. And here, these all, and all those which are at the red area, just see it, just see it, they all are on that area of the wave which is represented by a negative slope, or which it seems to be a negative slope, those vectors will be on those areas the particles are having the vectors in the upward direction. So in this way we can make a clear concept of the particles, that all the particles which yani all the waves have the particles at different position and their different direction of motion. So this is really important, that those all particles which are or which have the same position, it's not mandatory that they must have the same position only, their direction of motion matters a lot. Got it? Along with along with their uh, I can say along with their direction of motion, yeah, along with their position, what is important for them as well? Yeah, what is important? Their direction of motion. Okay, ji?
Yes.
So by this process I would like to reach to the topic of phase of a particle. Phase of a particle is position and direction of motion. Both describes the phase, whether the particles are in phase, whether the particles are out of phase, etc., etc. So all the particles of a wave with identical position, with identical position, with respect to equilibrium position and direction of motion are called in phase particles. This is really important, that in phase particles are those particles which have same direction of motion. Okay, same direction of motion, and what else? They have same position, right? So here I have mentioned some of the particles. Let's say particle number 0, then particle number 1, particle number 2, 3, 4, 5, 6, 7, 8, 9. There are several particles on this. So if I say that particle number 0, particle number 4, particle number 8, particle number 12, they all are at the same position. Similarly, particle number 1, 3, 9, 11, they all are at the same position. But do they have same direction of motion? Yes, yeah, yeah. Yeah, yeah, do you hear me?
Yes, sir.
Is Mohsin in the class? Mohsin?
Yeah, I guess.
Mohsin, are you in the class?
I mean, it just says Farira Farooq.
Yeah. Yeah. It's I think Mohsin, yes, it's Mohsin. So I was saying that particle number 1 and 3, although they are at the same position, but particle number 1 has downward direction of motion and particle number 3 has upward. That's why they are not in phase particles. Rather, particle number 1 and particle number 9. Do you see? They are at the same position from equilibrium. Yani they have been displaced at the same position from equilibrium, as well as they have the same direction of motion. That is why I can simply say that these particles are called in phase particles. That is why particle, yeah, I have mentioned this over here, that particle 1 and 3, they have same position but not direction. That's why they are out of phase. But particle 1 and 9, they have same position and same direction of motion. That is why they are in phase particles. So believe me, if you will have this concept clear, you will never get a confusion in phase, out of phase, and definitely in the next topic you have to study about the interference superposition. There, this would matter a lot. Okay. Got it?
Yes.
Okay, so here this is basically the representation of the wave. So when wave is represented, uh, one representation of the wave is that we can find or we can have its displacement and distance representation, and the second is its displacement and time representation. So these are basically two representations of a wave, in which one of them is displacement and distance, and the second one is displacement and time. Got it? So
Yes.
that representation in which the wave is having displacement versus distance, that gives you either amplitude and wavelength, the distance between two consecutive in phase points. Now, do you see I have added this word, right? In phase points. So it means in phase points are those points in which the waves have yani in which their direction of motion as well as their position is same. So I can say that particle number 1 and particle number 9, they are in phase points. So if I take the distance between these two particles, is it one wavelength or not? In the same way, particle number 2 and particle number 10, they are in phase points. So their distance is also equal to wavelength. So these are some important points what we have to learn. So from here, I told you that if x-axis is distance, then you will get wavelength. And if x-axis is time, you will get time period. Mind it, this is really, really important. You have to see it with open eyes, that whether x-axis is distance or time. So what is wavelength, by the way? Wavelength is total length divided by number of waves. For example, in this 6 centimeter, how many waves do I have? How many waves do I have?
One and a half.
Not one, one and a half.
Yeah,
So
I understand.
6 divided by one and a half, it means the wavelength of this wave is 4 centimeter. Right? How much? So just see it. If I say this black one is 1 centimeter, then 3 centimeter, 5 centimeter, then this is what? This is your 4 centimeters. So you can calculate wavelength from this graph. Is it clear?
Okay.
Okay, then we can find the time period if x-axis is your time. So time period is basically the distance, yeah, time interval between two in phase consecutive points, or two consecutive in phase points. Two consecutive in phase points. So here is that again. If you see, we just do it na, in our previous levels, that the distance between, sorry, the time between two peaks is time period, or the time to complete one wavelength or one wave is time period. So I can give you a formula here, that time is equals to total time divided by number of waves. What is time period? Total time divided by time period. So here, what is total time? There are 12 milliseconds. I have mentioned in milliseconds. And what is the number of waves in that? 1.5 waves. It means the time period of the wave is how much? 8 milliseconds. Is it clear to you?
Yes.
Okay. So that is why the frequency is actually the number of waves per cycle or per second. So frequency is total number of waves divided by total time taken. Total number of waves divided by total time taken. So here is uh, one important thing. What was time period? It was total time divided by number of waves. Is it? So can I say that frequency and time period, they are reciprocal to each other? because in frequency total number of waves are at the top and total time taken is down, and in the denominator, and in time period total time is at the numerator, and total number of waves is in denominator. So that is why you have this relation that frequency is 1 upon time period, or time period is 1 upon frequency. Is this all clear to you?
Yes.
Okay. So inshallah, in next topic, we will talk about the CRO, right? Okay, let's complete it. I believe that you will be able to handle that. CRO is that type of machine or that type of device which is used to figure out the wave, yani, which is used to read the wave. So in waves, you can read wavelength, you can read time period, you can read frequency, you can read amplitudes. Okay, so these are all properties which can be beta, oh, yes, in which you can say that they can all be demonstrated by your wave. They all can be demonstrated by your wave. So here wavelength is Ali, wavelength time period. This is your CRO dial. This CRO is basically a dial. CRO is a dial at which you have the grid, right? What you have? You have a grid. And on that grid, you can represent either x-axis or y-axis. So as I told you, that y-axis is basically the height of the wave. So it gives you the amplitude. It does not give you any other thing, right? Displacement or amplitude. And your x-axis is uh, x-axis is if it is represented by wavelength, or if it is representing your distance, it will give you wavelength, and if it is representing time, it will give you time period. So x-axis can be different, right? X-axis can be different. So when I move to uh, you know when I move to the CRO, in your CRO there are two controls. I mean, I have written it is zoom in and zoom out. So there are two controls in that, and those two control means that if you have to um, control that, or if you have to represent the wave in or with the help of this time-based setting or y gain, you can reduce the size of the wave. I mean, size, just apparent size, not the magnitude of the wave. And if you want to increase the zoom, yani when you want to zoom in mean you can increase the size. Oh yes. So to do that, what to do? Time base and y gain settings are reduced to enhance the size of the wave. Yani scale should be kept smaller. So this is simply the game of scale. So scale is kept smaller. So this is scale. So zoom out mean you will make the wave smaller. So time based setting and y gain setting is increased. So when you will keep a big scale, what will you have? You will have basically, it would be having a small size apparently. So this all is what you need, or what you have to learn in CRO. So if I believe that it will help you out to understand. In control of CRO, there are, I told you that there is on x-axis, the setting is time base, and time base settings tells you uh, that 1 division is equals to that value. For example, if the time base setting is 5 milliseconds per division, that shows that 1 division along x-axis is how much? 5 milliseconds. How much? 5 milliseconds, right? So we have to take care of this time based setting over there. And secondly, if I say what is y gain, so y gain is basically height of the wave or height of one division along y-axis. So along y-axis, if your wave, if the y gain setting is, let's say, okay, let me explain time based setting first, because that is a complete slide. Then you will move forward to your time base, sorry, y gain. So if I say that time based setting is 5 milliseconds, then you can find time period in this way. Time period can be equal to what? The value of time based setting. Okay, time based setting into length of one wave. Okay, length of one wave can be calculated in different ways. For example, if you go to this point, what is the length of one wave? How many divisions does it occupy? It occupies two divisions, right, on x-axis. So 1 centimeter is this, the height or width of this wave. So this is one division or 1 centimeter. So I can simply say that if time based setting is 5 millisecond, then one division is showing 5 millisecond, 10 milliseconds. So it one wave is completed in two divisions. So what is its time period? Its time period is 10 milliseconds. That's it. Simple word, simple technique to understand, to make it clear. Got it?
Yes, sir.
Okay, then the next is we have to know about the frequency. So frequency mein, what do? We just take inverse of time period. So when we take inverse of time period, first we have to calculate time period, then we take its inverse, and that is basically what, that is the calculations of your frequency. Got it? Okay, then y gain setting is basically height of the wave. So height of the wave mean when you have uh, the value of one division along along y-axis. Suppose it is 12 centimeter per centimeter, 12 volts per division. Then 1 centimeter along y-axis is equal to 12 centimeters. This is the scale, na? Simply, as I told you, this is what, this is your scale, right? Is it all clear to everyone?
Yes.
Okay, so you can find amplitudes of the wave by using y gain setting into peak to peak height divided by 2. Peak to peak height means you have to select the wave peak 1 and wave peak 2. So how many divisions are there from this? Let's say it is 1, 2, 3, 4. From here it is 1, 2, 3, 4, 5, and the other half over here, half over here. So it is 6. So 6 divisions are there, peak to peak. So you can divide it by 2. So you can make it that it is 6 divided by 2. 3 centimeter is its amplitude. So one division is representing 12. So 3 into 12, that is equal to basically 36 volt. This signal is of amplitude 36 volt. So this was basically the first lecture, lesson number 1, related to your waves. Inshallah, in next lesson we will talk about the entirely new concepts of the waves. They are the intensity of the wave and something like that. So please, I request you all that please make sure that your MCQs of the previous chapter should be completed meanwhile. Okay, because once I would complete this one, it would have a lot of working for itself, so it would not give you time. Okay, ji, see you inshallah.